In the Applied Facade Engineering course, we cover most of the materials commonly used in facades. This short case study course gives us an opportunity to explore concrete, timber and glass. We will also discuss some considerations regarding metals. Let's start with concrete. Concrete is fairly thermally conductive, and its contribution to the overall thermal performance of the building is negligible. For this reason, concrete is virtually always used in conjunction with insulating materials. In our case, the mineral wool insulation is used. To manage thermal bridges, the connections between existing facade and new primary framework will require thermal breaks. In the case when the entire building structure is retained, the concrete slab and beams connected to the external wall will need to be wrapped in insulation to address thermal bridging. In the Applied Facade Engineering course, we talk about the cube test, which is designed to test initial compressive strength, and the life cycle test of the concrete. Both tests are necessary for the new built precast concrete facades. In the case of existing facades, these tests could be substituted by the structural engineering report prepared by a qualified structural engineer who visits the building and describes any visible defects of the structure. Welbeck Street Car Park's concrete screen has been exposed to the external environment for the last 50 years, and all surfaces and connections are available for inspection. Judging from the photographs we took and those available online, the existing structure appears to be in a very good condition, with only minor stains on the surface. There are no visible cracks or rust stains anywhere. Concrete is brittle material. This should be considered when selecting fixings. All fixings to new or existing concrete should be pull-out tested. Another consideration when designing the connections is the location of the fixings relative to the existing rebars within the concrete panels and the distance between the edges of the concrete and the center of the fixings, commonly referred to as edge clearance distances. These parameters are crucial in the fixing selection process and when deciding on brackets configurations. Let's review the fixing selection process using the example of a scenario where the existing facade is disassembled and repurposed on the new primary framework in the form of window panel facade. 2 dead load brackets per panel are installed in the top horizontal part of the panel. It should be feasible to design the brackets so that the anchors are positioned in the middle of the horizontal part of the panel, avoiding rebars and being sufficiently far away from the edges. Mechanical expansion anchors could be considered for this application. These anchors work by expanding against the concrete when bolt is tightened. For the mechanical expansion anchors, manufacturers often recommend a minimum edge clearance distance of at least 5 anchors diameters to reduce the risk of concrete breakout. Since this bracket is pre-installed to the panels in the controlled environment, it may be permissible to add only 7 to 10 mm for the edge clearance distance to account for installation tolerances. When an expansion anchor is used in the in-situ concrete connection of the bracket, the same considerations apply regarding edge clearance distances and avoidance of clash with rebars. However, in-situ concrete should have more onerous edge clearance distance requirements. In addition to the edge clearance distance dimensions, designers should allow for a further 20 mm for the installation tolerances. For this reason, the edge clearance distance is virtually never shorter than 75 mm. The most challenging condition for selecting suitable fixings into the concrete is most likely to be a lateral restraint at the bottom of the panels. It is a sharp, narrow corner. Rebar connections are concentrated in this area, and the distance to the edges of the panel on either side are fairly close. Adhesive anchors, commonly referred to as chemical anchors, could be considered for this and similar applications. They generally allow for smaller edge distances than mechanical anchors because they spread the load more evenly and reduce the stress concentration. The minimum edge distance can be as low as 4 anchors diameters, but it is essential to follow the manufacturer's specifications as the performance of these anchors is highly dependent on the adhesive quality and the installation conditions. Chemical anchors are likely to be used for all connections to the repurposed precast concrete panels. For connections of the brackets to the new in-situ concrete, cast-in-place channels should be considered. These channels are connected to the rebars before concrete is poured. The edge distance often depends on the embedded part size and the expected load. It is not uncommon for the minimum edge clearance to be around 6 to 8 anchor diameters to ensure adequate performance without risking concrete spalling or cracking. Finally, screw anchors are likely to be used for fixing of the window to the existing precast concrete panels and for the fastening of the lightweight steel frame system, top and bottom tracks. Screw anchors typically require an edge clearance distance about 4 to 6 anchor diameters. This type of anchor is less susceptible to the edge effects than expansion anchors, but it is crucial to follow manufacturer recommendations to ensure performance. It is also crucial to verify concrete in situ fasteners by performing pull-out tests. Many aspects need to be considered when selecting glass for facades. This includes coating, which affects G value and U value of the glass. These parameters should align with the energy strategy of the building. It is always best to consult with glass manufacturer regarding the coating selection by providing them with the targeted energy values for the building. In terms of selecting appropriate composition of glazing units, it is crucial to perform glass risk analysis. This document is expected to be produced by the project facade consultant before tender stage and by the facade specialist contractor with the help of glass processor at the construction design stage. The facade specialist contractor and facade consultant are expected to perform structural finite element analysis to verify thickness and thermal treatment of the glass panes, while the glass processor is expected to conduct thermal safety analysis to verify whether the selected glasses are strong enough to withstand thermal shock. The glass used should be safe for both occupants and the public. In the options where windows are placed within the apertures of existing concrete screen, the outer pane of the glass should be laminated. This is important because the windows are located right above a busy street and pavement. If the outer pane breaks due to impact or thermal shock, the glass pieces can fall onto pedestrians below, leading to serious injuries. Even if the outer glass is monolithic heat-soak tested toughened glass, which is expected to break into smaller pieces, these particles may still fall in clusters and pose serious risk to pedestrians. It goes without saying that the use of monolithic annealed or heat-strengthened monolithic glass externally, especially above area accessible to public or service personnel, is not permissible. The internal pane of glass in this case could be monolithic toughened. It is located at the same level as the building occupants, and in case of breakage, it may inflict minor cuts on the building users. However, the risk of serious injuries is considered to be negligible. This glass is accessible to occupants, so it cannot be monolithic annealed or heat-strengthened. There is one scenario when the use of monolithic toughened glass could be deemed permissible if used externally. It may be permissible to use monolithic heat-soak tested toughened glass externally in the curtain wall behind the concrete screen. In case of breakage, small pieces of glass will fall onto balcony decking. The risk of injuries to the public on the pavement below is minimal. In all application areas, the use of laminated glass internally and externally would be a more risk-averse option. Let's briefly touch upon metals in this case study. We have chosen aluminium for all windows, doors, curtain wall, rainwater goods profiles, as well as decking and cladding to balcony soffits. It is sufficiently resistant to corrosion, so it's suitable for use in external environment applications. Since the building is not located in the marine environment, powder coating is suitable for the finish treatment of aluminium profiles. However, a more expensive anodized finish would offer better corrosion resistance. The lightweight steel frame behind concrete panels, as well as curtain wall backing pan, are positioned in the dry zone. It should be acceptable for these elements to be made out of light-gauge galvanized steel. However, these elements need to be adequately protected against corrosion, which may result from interstitial condensation. We will discuss this in the building physics module of the course. The brackets of concrete panels, as well as fixings and anchors, are made of stainless steel. Balcony hot-rolled steel frame is covered by aluminium decking and soffit. It is somewhat protected from rainwater, however, it is still considered to be exposed to the external environment. Being made of larger size steel sections, it is expected to be at least 6 mm thick. That means that it is possible to achieve a sufficient galvanized coating of about 85 microns, which is expected to last more than 60 years, according to the corrosion map on the Galvanizers Association website. When it comes to balcony balustrades, designers should consider aluminium or stainless steel. Balustrade sections may not be thick enough to achieve a sufficient thickness of the galvanizing coating, and it may not last for a whole duration of the building expected design and service life. Here is an example of a similar style balustrade condition 10 years after the completion of the facade. As you can see, corrosion took its toll in this short period of time. So far, it is just a cosmetic finish failure. However, it is clear that the balustrade will not last for 60 years. To avoid bimetallic corrosion, any dissimilar metals should be separated. For example, the aluminium subframe of the soffit and decking are separated from the galvanized steel sections with PVC pads or a PDM gasket. We will talk about thermal expansion of metals and how to account for it in the movement and tolerances module of this course. Lastly, we should talk about mass timber used in our case study. In the parts of facade module, we discussed the balcony connection to the cross-laminated timber slab. We have already mentioned that timber can rot if exposed to moisture. Therefore, weather detailing around connections to timber and any facade penetrations, as well as the management of interstitial condensations, are critical. Mass timber structures are most vulnerable to water ingress during construction. All reasonable precautions should be taken to protect timber structures from elements during the transportation and assembly of the parts on site. However, given the significant amount of rainfall in London, it is virtually impossible to erect a 7-story timber structure without any of its parts getting wet. For this reason, provision should be made for compromised timber sections to dry before they are covered up with the facade and internal finishes. Timber is a combustible material. When it is used as a primary framework, it should be protected by fire-rated materials. For compliance purposes, its presence in the external walls of tall buildings should be minimized. We will talk about this in the fire safety module. Covering mass timber parts with gypsum boards, mineral wool and concrete also helps with the acoustic performance. Timber shrinkage and how it can be accommodated will be discussed in the movement and tolerances module. Course participants are recommended to take the Applied Facade Engineering course, where we delve into greater detail on these and other materials commonly used in facades.